Hello, I'm Edgar, and this video will demonstrate my approach to the design and implementation of systems in Wwise and Unreal Engine to demonstrate technical sound designer skills. The level is a shooter game template from Epic Games, and the implementation was mostly done via blueprint programming, but on several occasions basic C++ programming was also done. All the original sounds were disabled and replaced with my own. However, the approach leans more towards the technical sound design skill set than the sound designer role. As such, more time was dedicated into designing, implementing, and perfecting systems. Overall, the level was approached as a sandbox environment to implement and program systems and sounds, and some debugs were left on for better understanding. The video will be divided into 5 parts matching soundscape categories and other related processes: ambience, player, weapon, buzzes and spatial audio, and optimization. Area loops were implemented via a spline and spot triggers. The spline blueprint was adapted from a blueprint original created by the sound designer Troels Nygaard in his blog post at Audiokinetic. The goal was to attach an emitter into a spline that will follow the player. This reduces the total amount of emitters needed to populate the background ambience. In the project, this was used to play the wind at the edge of the map and a barrier sound. The original blueprint is set up for a variety of functions, but in the project, only the player tracking location, Wwise, and debug nodes are being used. In Wwise, a single loop file was imported and several modulators with random parameters were added to provide variation over time, such as volume, pitch, and EQ. Moreover, the blueprint was reused to set an overlap trigger in the barrier source loop that uses a spline. For this, a bool and a Wwise event was set as a public variables that needs to be set in the actor. The barrier uses a trigger box to play an entry type sound effect, and in Wwise the event has several RTPCs linking the player distance with a blend container to change the sound. After the overall ambience was populated, an empty zone was identified and a timed sound trigger was added in case the player stays there for longer periods of time. The idea was to expand the edge of the map's spline emitter radius dynamically and add flying car sound. For this, a blueprint was set to play the event with a trigger box and a timeline node to randomly select a cooldown timer, given that shooting or moving out of the trigger box fades out the ambience. The trigger box also sends an event to the spline blueprint, telling it to increase the attenuation radius with a timeline node. In Wwise, smaller audio files were imported into a random container with the Wwise Silence SFX to introduce cooldowns. Then 3D position automation lanes were designed to create a static yet specialized ambience that crossed the stereo field based on the listener. A similar approach was taken to the wind gusts. Lastly, the wind gusts were implemented via an overlap trigger scripted in C++. Functions were declared in the header file and then called as a method in the source file inside the actor class. The rest of the ambience is made up with source loop emitters and share a similar implementation approach. Panels and terminals both have public variables which can change their behavior while using the same blueprint. For instance, terminals can play one out of 3 option sound sequence. Furthermore, a timed interaction system was designed for the terminals. If the player interacts with a terminal that has a bool set to true, it will play a pre-made sequence. Otherwise, it will play random beeps. Everything was set up with random delays in blueprints to prevent repetition. It was imagined the player wearing an exoskeleton armor, and towards that, footsteps and movement sounds were designed to be heavier and more robotic. Also, two systems were designed to dynamically change the movement sounds based on landing and climbing, to further highlight the armor. Footsteps were implemented in the animation blueprint using anim notifies as a trigger from the animation. Here, a line trace pointing downwards detects a physical material to change the Y switch and play the corresponding switch container. The folding system is guided by a RTPC and was programmed to only consider folding distances greater than the ones from regular jumping. This is calculated using a ray trace and player velocity that is then clamped to fit the RTPC scale and can be further mapped to other parameters. Currently is set to decrease the pitch and increase the volume that pairs well with another set of switch containers that change the landing sound. Similarly, the air steam brakes only activates when the player is falling from even greater distances. Because the line trace was not reliable to check if the player is falling, as it can happen for example when the player is off center on top of a wall, a bool was created to serve as a second condition. Four physical materials were created and mapped to switches for footsteps, landing sounds, and bullet impacts, which are metal, concrete, glass, and brass. Next is the going up or climbing mechanic. The goal was to provide a sense of a movement strain from the armor when the player is walking on steeper angles. The basis of this system was adapted from an existing blueprint. However, instead of changing movement speed, it was mapped into an RTPC that can be further expanded sound design wise. Currently changes the low pass filter, pitch, volume, and effects dry to wet ratio. And also, interpolation values of the RTPC were fine-tuned to prevent being changed on minor angles and return to normal after the climb. For the system to work, a set of bools were set to make sure the player is moving. After, it uses two line traces pointed downwards to calculate the pitch rotation value, that is, up and down. Then, the difference is passed onto a curved object to control the RTPC value. Majority of the weapon-wise events were hooked to the weapon C++ scripts and the logic programmed in the corresponding blueprint. This was done as a workaround to implement wise events given that the weapon shooting systems are hard-coded in the code. In the weapon-related header files, it was set a custom blueprint implementable method that is then called by the game code. First, the last shot RTPC. The rifle has RTPC linked to the current ammo that is set to gradually increase the pitch and the low pass filter. When the ammo reaches 1, a wise event is played to communicate the last shot was fired. To implement the bullet impact, several approaches were attempted, including using Wwise set switch methods in C++. However, given the complexity of the code and how it was set, all physical materials were set back to default and the workaround was designed in Blueprint. Events were created in Wwise to set a switch and then added to the code switch statement. The rocket launcher follows a similar implementation approach as the rifle, but it doesn't have a last shot system. Instead, it was designed an overheat-like system that plays if the player shoots 3 times and doesn't reload. This will trigger a short sound that will stop after looping twice or until the player reloads. Buzzes were created and special audio techniques set to further elevate the audio experience. All major categories of sounds were grouped into a buzz in which it is possible to control, apply parameters, and mix simultaneously. In the project, a state was set to lower the ambient sounds whenever the player aims with right click. Several spatial audio volumes and portals were set into the level and then routed to the corresponding buses. These volumes were applied to provide different acoustic properties to the small boxes, the underground room, outside space, and the tunnel. Likewise, some of these volumes have reflectors with acoustic textures on to reflect sounds filtered according to the acoustic material. This process was achieved with the Wwise Reflect plugin. The last process in the project was the optimization using several profiler windows in Wwise. First, all sounds were converted into the Vorbis format, and then the threshold set towards the virtual was reduced to -. After, the window was set to stream from disk, reducing the sound bank size, and these were divided into categories from the start. Likewise, several sound assets were added. Processes resulted in the reduction of the overall active in the worst-case tested scenario of 20 physical active processes. Similarly, processing time was also cut to account for the processing-heavy usage of the spatial features such as the reflector, resulting in a peak of 3.4 milliseconds.